And that's why you're here. I read the article on Wikipedia.
And checked who wrote it. And
And
then he found my stuff. So, but it's not my invention, not at all. For those of you who know, BitTorrent uses a hash list. Many other modern peer-to-peer networks use a hash tree, but I'll explain it. If we have our blocks, we make a hash of each of them. Just a regular hash sum. So this might be 1 megabyte blocks, and this is 20 bytes then, of course, SHA-1 or so. Or it might be some other hash sum. And these ones we put in a file together. It just becomes a list of them. And that list is stored in a .torrent file. Most of you have probably said a torrent file. Yeah. So the torrent file actually contains a list of hashes like this of all the blocks. And that is a hash list. It's fairly simple. Sometimes we do that now also on BitTorrent. They didn't do it originally, but we can take a hash of all of these ones. I call that a top hash, others call it like a root hash. It has many names. And you know it has magnet links. Magnet links actually is the hash. Actually, it's not hash just of the hashes, it's also the other data in the torrent file. But all the metadata in the torrent file, like the file name, all the file names of all the files in that download, in that torrent. Yeah. So all the metadata hash it, and this top hash you can publish. So all you need really is the top hash, the magnet link. And then you can look that one up if you have a distributed hash table or some other lookup system. Look up nodes that are taking part in that file sharing swarm, and then ask them for the torrent file. That is for the hash list. And they give you the hash list, and with the hash summary you can check that they actually give you a correct hash list, that they're not tricking you or very buggy. And then when you have all these hashes, you can start downloading blocks and check the blocks one by one. And I think all of you know, the reason that to hash blocks is, if you download the whole file, if you just had one hash, you have to download the entire file and start over if it was wrong. Here you can download 1 megabyte at a time and check it. Now, people thought that, like, how big should we have the blocks? Because there's a trade-off. If you have many blocks, it becomes many hashes, so the torrent file gets big. So you don't want a too big hash list. And the other way is to have small blocks, the big blocks, but then the blocks, so the hash list becomes short, but then the blocks becomes too big. So, well, they didn't invent it for that purpose, but the Merkle tree was already invented in the 70s for another purpose. And we should talk about that purpose too, I think. And he realized you can make a tree. So, I don't remember what image I used for that tree. I made that image on Wikipedia, but that was long ago. Yeah. We'll write it upside down now, since we already started upside down. So, this one, is it? Yeah, okay, thank you. It was like 10 years ago I made it, so. Something like that. Instead of just hashing the hash list, you hash each two of them to new hash, get a shorter hash list, and then you hash them 2 and 2 until you get just one. So it's a tree of hashes.
You concatenate the hashes first.
You concatenate those two and hash them. Yeah. And you concatenate those two and hash that. And then you concatenate those two and so on. And you do it not just 2 or 3 levels, you do it on lots of levels. And that means you can have these blocks be just, for instance, 1 kilobyte, which is very small today. And the tree gets pretty big, but still you only have one top hash. And that top hash you can put in a magnet link, for instance, and then download the tree from any node and start downloading blocks. But this has some neat features. But
use it up for mobile sync.
For
mobile synchronization actually uses Merkle trees a lot, using a reverse Merkle tree on the client side.
Yeah.
They use it like in file systems as well.
I think Page2B uses it. I think.
ZFS uses
React Mobile uses it.
Yeah, because you can compare sub-elements within the tree, which is the join that you can. If that was a file system, if that top block is a file system, you can see if there's any changes within the sub-branches of the tree as well.
Yeah, it's used for file systems. It was used already in the 70s for file systems. For some, I don't know what kind of people, but it was also to verify external random access memory in some platform.
Being for synchronizing level
That was
DB.
originally used for security.
Yeah, I probably will talk about that one because it's a bit interesting in cryptography. If you guys are interested in cryptography.
Yes.
Yes, okay. The thing with Merkle trees or hash trees are really that you can actually download a part of the tree instead of an entire tree. So you can download, for instance, this part. Well, this tree is so small, but you don't have to download those two. If you have this part, and of course you already know the top hash from the trusted source, they can verify this part of the tree. You will know that if you hash those two and get the right result, those two are true. Then you can check that those are true. And then you can start downloading those blocks, even if you don't have the entire tree. That's the original purpose of hash trees, to be able to have huge trees and get one branch and get started. The problem is, today most peer-to-peer networks, they haven't implemented the branch handling. They just get the whole hash tree at once from one node. And then that's useless. Then it would be simpler to use a hash list and actually take less bandwidth.
Yeah.
So hash lists would actually be better then. So they haven't understood the purpose of it. Because probably, I haven't tried to code that. It's probably fairly, it takes some time to code that and debug it, so I really didn't bother to try. But anyway, that's the purpose of it. When I looked at this early on, I tried to see if I could use just I thought, well, the tree was too messy, so I thought just use 2 levels and started counting on that, and then I realized 1 level, just a plain hash list, is correct if you have a good formula for knowing what size of the blocks you need. I don't remember the formula by heart now, but if you check, if you adapt the number of blocks compared to the file size in a smart way, you get my goal was the formula I invented was the whole hash list should have the same size as 1 block. Because you download the hash list first from one node, like 1 block, and then you start downloading blocks, and you want to wait about the same time before you check the block. So I want the hash list to be the same size as the blocks. And when I made the formula for that, to get exactly that, I realized that the block size that I ended up with, for any file size, is the exact right block size for the internet speed that most people have that download that size of file. So people downloading small music files, they usually are really slow connections, and they get very small blocks automatically because it's so short. But for those downloading movies of the size 700 megabytes, they get a bigger block size, and those downloading 8 gigabytes or bigger, those they have really fast DSL usually. So the block sizes automatically became the right size. So with that formula, if you design the formula so the hash list is the same length as the block size, then you get a decent block size that you can use for any speed. It just fits. So it seems the hash tree is kind of overkill for normal users. So by pure luck, we can stick with a hash list and just be smart about choosing block size. So I'm sorry I don't have that formula in my head, but probably you guys can do math, so you can do that. Put up the formula, see what you need, how to transfer, how to calculate the block size. That's based on that I was using SHA-1, so it was 20-byte hashes. But you get pretty much the same result with a 32-byte hash, or like a SHA-256, so it gets pretty much the same result. So I actually say, if you're lazy and it's good enough, then hash lists are good enough, so just pick the block size correctly. Okay. Well, I could perhaps mention why. I should mention the hash trees, why they were invented. So hash tree and Merkle tree is the same thing. back in the 70s, when they had invented public key cryptography, they realized that public key cryptography is really bad. It's very bad encryption, actually. It's very weak. That's why we need huge keys for public key cryptography. What's the name of the most common? That is all. Sorry?
Oh, RSA?
RSA, yeah. For instance, RSA uses like 4 kilobyte, there's 4,000 bit keys now or something normally to be strong enough. So it's ridiculous, and it's really, really slow. So usually we just encrypt very small things with it. But I won't get into that part. But, and also they realized the day we get quantum computers, those are screwed. All the public key cryptography systems are screwed. So, but there was one kind of signature scheme at least. Do you know what cryptographic signatures are? Everyone knows that? Okay. Cryptographic signatures can be done with only hashes, without public key cryptography. That's Lamport signatures. So with a Lamport signature, you can sign one file. If you have one Lamport signature, you pre-publish a hash, and I shouldn't explain exactly how they work, but I can give you a hash, and 10 years later, I can use that my secret data about that hash to sign it, and you can check it with that hash. And you can read on Wikipedia how it works, but you don't really need to understand how it works. It's fairly simple, but still, you have to read it 3 times through or something to grasp it.
But it's only a one-time.
It's a one-time signature, so that hash I gave you can be only used once to sign one file, and then I can never reuse it.
What happens if you did reuse it?
After I've used it, anyone can. If I reuse it, I will reveal more parts of my secret data, and then someone can actually fake a third file.
Right.
Actually,
you use it once, but if you only use it once, they won't be able to do that.
Yeah. So if I do it twice, perhaps it can still not really do, because then I haven't revealed all of the bits.
Right.
But if I do it a couple of times, they will have enough bits to be able to combine the file.
Because it's the fact that you haven't used all of the bits in the secret.
All of the secret bits, yeah. I think it was a long time ago. Anyway, this one can be used once, but then Mr. Merkle realized that you can make a Merkle tree or a hash tree, all these hashes, and put the Lamport hashes here. Once, lots of them, I can make 1 million of them beforehand, and then make a hash tree with them. And just publish the top hash. And when I send you a file that I've signed, I send, you know, or they know this one, I send you the branch up to the hash, the Lamport hash that I actually used to sign this file. So that's the purpose of it. Really, you don't need to understand this exactly, but my point is, big hashes cannot be cracked by quantum computers. Quantum computers can't crack symmetric cryptography, like, what's the common names of AES and stuff like that. They can actually crack it slightly better than normal computers, so we need to use slightly stronger hashes, slightly stronger, perhaps AES a bit too weak then, but if you 2 layers of AES, and you will be good even when we get quantum computers. So Lamport signatures will survive quantum computers, and with Merkle trees, they get fairly practical. So you can still sign stuff then. And we can still encrypt stuff too, of course, with symmetric cryptography. Yeah. Oh, while we're at it. Most of you know what a certificate of authority means. Certificates on public, certificates with public keys and everything in. People think that a CA, how do you pronounce that? CA has to use public key cryptography. That's not true. You can actually build a CA with certificates and everything only based on symmetric cryptography. When they did that in the 70s, they invented something called, I must forget the name, that dog with all the heads in the Greek. Sir? Cerberus, thank you. How do you spell that? C. Okay. It was spelled with a K in Swedish.
Yeah, Cerberus.
Cerberus or Cerberus or Kerberos?
It's Cerberus in English, but Cerberus is the Unix.
Okay, Kerberos. Kerberos system is actually a CA system, they can issue keys to nodes and all that. But originally it was just used to give people permissions. But you can also use it to encrypt communication between nodes, to give them the keys to be able to talk with each other. I don't really should spend the time explaining exactly how it works, but it only uses symmetric key cryptography. So this one will survive quantum computing also.
It will still be really slow.
No, it's not.
The ones I've used are typically really slow.
So,
The Kerberos services I've used are really slow.
okay, then there's bad
And they have
implementation
security
because
patches coming out every
you
week.
can make it really fast if you like to.
Those ones.
You can make it really fast. So then it's bad implementation. So everything that we do with almost everything, not exactly, but almost everything we do with public key cryptography can be done with hashes and symmetric key cryptography. So we will survive quantum computing. I like just to share that because that's a happy thought, I think. And so you know what to look for that if that day comes. Actually, one reason that I'm here today is because of this, because in 1999 I worked for General Motors, and they had problems with people hacking their own cars, which actually is a problem because they increase the engine power and destroy the gearbox, and then they switch back to the original software.